Yes, we can.
Great.
Go for it.
Um, so yeah, I'm presenting on a discrete event simulation model for the optimal testing for routine monitoring in chronic conditions. I've put the GitHub link at the bottom here if anyone wants to follow the code in GitHub. Um, don't know if I can paste it into the chat or not. Um, uh, okay. Anyway, it'll be at the end as well. So the background to this is that long-term monitoring is vital in managing long-term conditions, which we're going to call LTCs. But there's currently no robust evidence to inform recommendations on the selection of tests or the test frequency to monitor people with LTCs in primary care in the UK. Under-testing may delay detection of events and adaptation of treatment, but higher frequency of monitoring does not necessarily lead to better management. So we aimed to explore what is the most cost-effective panel of blood tests and frequency of testing for UK patients with type 2 diabetes, hypertension, or chronic kidney disease in a primary care setting. And we used a discrete event simulation to do this, to model the risk factors and events they may have. And in our model, the event rates depend on the risk factors, and then the events in turn will affect the risk factors. Our risk factor trajectories were informed by CPRD data, and the survival models for events were also estimated using CPRD, and other inputs were informed by targeted literature searches and expert opinion. So here are the risk factor trajectories that we included in our model. We modeled them either using a linear mixed effects model or a linear mixed effects autoregression model, depending on what was a better fit. And for the linear mixed effects model, we calculated the risk factor Y for patient I at time t using this equation, where the alpha, beta, and gammas were sampled once per PSA sample, and the epsilons and omega were sampled once per patient per PSA sample. And here are the events that we included in our model. The risk factor measurement times, by which we mean blood test times, were set in advance. For example, for CKD, our testing strategies were no testing, testing HbA1c, eGFR, and hemoglobin every 6 months or every year. And then we also looked at whether we should test for potassium and lipids. All other events in the model were modeled using exponential survival models. And the log rates for the events in these models depended on the latest risk factor values. So due to the complexity of our model, we were unable to use existing DES model R packages that were available when we first started writing our code. So instead, we took the approach to code our model in base R. We've written 18 functions to modularize our code, and these included functions to generate risk factor trajectory parameters, generate event log rates dependent on a patient's current risk factors, and update the risk factor trajectory parameters in response to events. Here's our model structure. We start with the model setup that's done every time, and then we'll go into the loop over patients. So we sample their baseline characteristics. Then we go into our loop over all the time points in the model. So we'll simulate times until each possible event. We then resolve the computed risks and select the event that occurs first. We then evaluate that event, including any response interventions, for example, a medication or a lifestyle change. And these would then be affecting the alphas and betas in the linear mixed effects model. So those trajectories then change. And then we update our risk factor levels for that patient at that time point, and then go around again simulating times for each possible event. I don't have time to talk through all the functions, but here in pink, we've got the functions that we used at different points in our model. The main setup of the model is in the main setup, we create a time to event array and a risk factor array. And the time to event array saves what events happen at what times and also what actions were taken. So we create that array, and then after we've run the model, we then in separate functions generate the patient costs and queries. As it was easier to do it this way because some of the costs sort of start at one point and continue for the rest of the model, whereas some of them would last a particular length of time. And it also meant that when I was debugging the code, I could sort of sort out one bit and then sort the other bit without messing up, without having to like rerun the first bit. So yeah, this was our model setup. So we set up, like, define our risk factor names, which some of them were included for all LTCs, but others were LTC specific. So we wrote the code to handle that. And we also defined the blood test times in advance. And then sort of, yeah, create those empty arrays and then are ready to run the model. The other more complicated step in the model is the evaluating of events. So for example, an anemia can either happen as an event from the survival model, which is in this blue box at the top. And so if that event is the event that happens, we'll then trigger this action called action HGB for action hemoglobin. But we might also trigger that same action if someone's low iron levels were picked up by a blood test. So it's saying if we'd done a blood test at this time, then we'll look at to see what the current hemoglobin is. And that would also trigger the same action HGB function. And then we have a thing, like another bit later, that then says if this action has happened, then we need to make changes to the trajectories. And we needed to do it like this because some of the trajectories could be, like, actions could be triggered by more than one event. And we needed to make sure we weren't sort of doubly making the same change to a trajectory at a single time point. So as a more of a picture way of showing it, for anemia, in the purple line going across here, we're saying that this is if there was a blood test that measured that you had low hemoglobin. So this is working via the trajectory. That would then lead to changes in the hemoglobin trajectory. Alternatively, it might be that the trajectory value, like risk factors, then feed into the spiral equation, which then means you've got a higher chance of anemia. And if you had anemia, then you'd also get changes in costs related to that. And then we have hemoglobin trajectory changes that then feed back to the beginning with the hemoglobin trajectory, where we're changing some of the parameters of that. This is one of the simpler ones because, yeah, when we have lipids and HbA1c, they're associated with more events and also they both change at the same time. We run this model using an HPC, and this was, yeah, good, as it meant that we could run multiple jobs at once. And we ran each PSA as a separate job on the HPC. We're doing 1,000 PSAs for each testing strategy. And we had 8 to 10 testing strategies per LTC, which meant that this was 26,000 HPC jobs in total. To do this in a sort of straightforward way, we have a bit at the top of our sort of generic main analysis script, where in the original, like the generic version, we have LTC is X, test strategy name is Y, and the PSA is ZZZ. And in order to run the script, we need to convert it into something that looks more like this. So we've selected CKD testing strategy B and say this is PSA number 1. So we did this in Linux on the HPC. So first I had a job where I roll out all of the testing strategies. So I've got this generic testing strategy job script, and then I create a version of it, like CKD version A, CKD strategy B, CKD strategy C. And what this does is it turns the top generic job script into the bottom CKD specific job script. So where before we had something that was saying change XXX to, there's a lot of letters in this, AAA, we now have it's changing XXX to CKD, and it's using the right testing strategy as well. And then we've also got this slurm array task ID, which when we run the job, the HPC will fill it in with numbers 1 to 1,000. As then we're then able to use this bottom script to then change, I can go back, this to this. That's what we do with the bottom script. And it means that I can then sort of rerun the analysis by just like running 3 jobs, which makes it a lot easier. We also need to work out a way to set seeds to be consistent, as we want some things to be this specific to PSA and LTC, and then some of them we want to be specific to patient. So I did this by creating a seed that was dependent on the LTC and also the PSA number. And then here I did one that was also dependent on the patient ID, which meant that we could get consistency where it's needed. Briefly going into some results, there is a lot of uncertainty in this model as it was an ambitious question to answer. So we've got some results, but we have very wide credible intervals. We were asking questions like looking at things like how frequently we should test. So on the left here, we're comparing testing strategies of A, never testing, B, testing 6 monthly, C, testing yearly. So we can see that testing 6 monthly has the highest probability of being most cost effective there. And then we also compared testing strategies C and D. So the difference here was D does contain lipids and C doesn't. And then we got a more sort of conclusive one here where we looked at B without potassium and G with potassium. So we're able to use the testing strategies to explore different questions. So to summarize, this is a very complex decision problem to model, and therefore we've made a lot of assumptions and choices, and we have a very long list of limitations. We coded the model in base R as we were unable to use existing DES model R packages that were available when we started writing the code, due to the complex interconnections between risk trajectories and events in our model. And we performed our analysis in R on a high-performance computing system, which made it feasible to compare multiple monitoring strategies for each LTC. And thanks to Howard Thom, who is my line manager on this project and the senior health economist on it, and then also our other collaborators in Bristol and the wider team for this optimal testing project. And again, I've got my GitHub list linked to the public version there. Thanks.
Excellent, Mary. Thank you very much. Please put any questions on the chat or raise your hand if you have any questions for Mary. I'll probably kick things off. And on your point in the middle, on your summary about when you say that existing DES R packages were not usable, you sort of hit on that point, but what was the main reason for that? Was it the model structure, performance limitations, or the lack of flexibility in handling those interdependencies between the risk trajectories, equations, and events? What was the reason?
I think the main reason was the interdependence between risk trajectories and event rates. We also have quite a lot of us sort of caveats or whatever to our model. So like some events can only happen once, or some things last a certain amount of time, or other things. I guess that can probably be handled by package, but it wasn't just a sort of write a few equations, run the model, it was write a few equations and then say, but actually we do this differently and this differently and this differently. So it made it sort of longer.
Okay, that makes sense. Thank you. And we have a question from Yaning Wu. Have you incorporated challenges in patients' adherence to regular, example, 6 months testing within this model? And how important do you think it is to incorporate these?
We haven't incorporated that. It would be a useful question to ask, but I think the model already has so many sort of limitations and assumptions that it's probably not worth asking it on top of this version of the model, but maybe as a separate question. Yeah.
Yeah, potentially something to explore on the site. And last question from Josie Dodd. Apologies, we're running out of time. Have you considered including a system for managing limited resource use in the model? For example, what was described by Javier earlier?
No, we haven't included that. That would be useful to look at. We'd need a lot more data. At the moment, we assume that someone can get a blood test whenever they want, which I think the NHS can, mostly manages, but we also assume that someone can get a transplant whenever they want as well. So that would be less realistic. But yeah, this model's got a lot of simplifications.
Okay, great. Let's thank again Mary for a great presentation. Thanks very much, Mary.